So as we look at respiration, right, respiration can actually mean a few different things here. So what we do is we separate this into external respiration, and this line's kind of hard to see for you, right? But internal respiration, okay? In external respiration, what we're looking at is actual pulmonary ventilation. And we'll go through each of these in more detail, but pulmonary ventilation is how we're actually moving air in and out of the lungs. Also included then is gas diffusion. And so what we're talking about in external respiration, we mean the gas diffusion from the alveoli into the bloodstream, right, into those capillaries, and also the gas diffusion from the bloodstream, right, out of the capillaries and into the tissues. So alveoli to capillaries, and then also capillaries into those tissues. We also have gas transport. Right. So we see us moving oxygen towards the tissues and then CO2 away from the tissues. That is all included in what we call external respiration. Internal respiration then is really just referring to, right, so we can use our adipocyte here, that oxygen crossing into the cell, right, diffusing across that cell membrane, or the CO2 that's crossing out of the cell. So internal, we're thinking at the cellular level. Now, what goes on inside of this tissue? We take oxygen and we do what process? Cellular respiration. Don't worry, we get a whole chapter. Chapter 25 talks about cellular respiration. How does the cell use oxygen and produce this waste product, CO2, right? That is internal respiration. So let's look more at these factors that make up external respiration. Okay, so our first one here, pulmonary ventilation. Now, there's a few things that you need to know in order for pulmonary ventilation to make sense. The first of those is that air is always going to move from an area of higher pressure to an area of lower pressure. High pressure to low pressure. You're excited, you're like, that sounds like diffusion, right? High concentration to low concentration. And you've already also experienced this, right? If you think about blowing up a balloon, right? That balloon now has high pressure. If you open the, undo the knot, whew, that air moves right out. It goes from an area of high pressure to low pressure. Okay, so we've already got this. Now, where it gets a little more complicated is they throw some physics in here. So we start talking about Boyle's law. And Boyle's law says that pressure and volume are inversely related, right? Pressure and volume are inversely related, right? So as pressure goes up, volume goes down. Did I do that right? As volume goes up, pressure goes down, right? If we look at Boyle's law, let's think this through. Pressure is inversely related to volume. So absolutely. So what they're showing here is if as you decrease the volume of the container, you increase the pressure, right? You have more molecules squished tighter together. Does that kind of make sense? And as we increase the volume of the container here, the pressure goes down. There we go. That makes more sense. Okay? So Boyle's law sounds complicated, but it really, I mean, it's pretty straightforward, right, if you think it through. But this is actually what the lung is going to function based off of, right? So we are going to change the volume of the lung to change, right, we change the volume of the lung to change the pressure, and that is going to determine our airflow, because air always goes from high pressure to low pressure. Now, the other thing to keep in mind here is this chapter talks an awful lot about atmospheric pressure. And so a couple things to keep in mind. Atmospheric pressure, right? So at sea level, you live under 1 atmosphere. And what they mean by this, right, is if you are standing, standing at sea level, you have sitting on top of you, right, the whole atmosphere, this column of air pressing down on you. And so we say that weighs 1 atmosphere. You're either really strong or it's really light. Okay? The other thing you'll see then is that is equivalent to 760 millimeters of mercury. So basically you can measure barometric pressure. You can measure how much the atmosphere weighs, right, by how much, say, mercury gets displaced in a barometer, 760. Now, 1 atmosphere is a very convenient term, but we're going to be using such small changes in pressure that this 760 is actually going to get used a lot in here, right? Because when you breathe, right, all you really need to do is increase the volume of the lung enough that the pressure drops just below this, 759, air will come rushing in. So let's look at this. So when we talk about inhalation on this side here, notice what happens. So the diaphragm that's up here contracts, and the ribs and sternum elevate, right? That increases the volume. So you increase the volume. How? By contracting the diaphragm and lifting the ribs. Lift the thoracic cage. And that increases volume. When you increase volume, what happens to pressure? You decrease the pressure, right? And so that's what they're showing you here, is that the pressure outside is still at 760 millimeters of mercury. The pressure inside, if it's now at 759, 760 outside is greater than 759, air is going to flow in. High pressure to lower pressure, we get airflow. Okay? Now, at rest, it really can be this small of a change in pressures. Athletes are able to create changes that are more like 30 millimeters of mercury difference to really get air flowing into the lungs. Now, on this side, they're showing exhalation. Okay? Now, at rest, exhalation is a very passive process. We'll talk more about what the lung tissue is like, but there's actually a lot of elastic tissue in there. And so as that lung kind of springs back, that is going to basically return our volume to normal. So we decrease the volume of the lung, right? So the diaphragm comes back into place, the rib cage relaxes, that increases the pressure of our lungs, and that makes it so that the pressure outside is less than the pressure inside. Again, this can be a really small change. They're just showing 760 always on the outside is less than, say, 761, right? That's all you need for airflow to go from an area of high pressure, in this case inside the lung, to the lower pressure outside the lung. That's all exhalation is. So this will help us as we think about the lung. The expandability of the lung is actually really important. And this is something, there's certain conditions, but definitely aging. As that thoracic cage maybe gets a little bit stiffer, as the lungs become less compliant, they become less stretchy and maybe less easy to recoil, that's going to affect the way that we're able to inhale and exhale. Okay? But under normal conditions, right, this does not require much change in pressure. Now, one more thing, just to make it a little more complicated, is that was a simplification, right? Because the lung is not actually attached to the diaphragm. The lung sits in the pleural cavity, right? You have these two pleural cavities, these serous membranes that sit outside the lung, just like the pericardium, and it's actually that pleural membrane that's glued to the diaphragm. And so, without getting too crazy, right, all they're trying to show us is that when the diaphragm contracts, right, we actually pull on that pleura. We change what they call the intrapleural pressure, and that changes the pressure inside of the lung. The only reason I point this out is that if that pleural membrane gets damaged, either from like a gunshot or a stab wound on the outside, or sometimes they call it a bleb, the actual surface of the lung, right? That serous, the visceral side of that serous membrane can get damaged from a bleb. If you lose the continuity of that pleural membrane, you can have what's called a pneumothorax. As soon as you can't create that suction, that pressure in this pleural membrane, your lung is going to collapse. You're not going to be able to turn contractions of the diaphragm into changes of pressure inside of the lung. So then the volume of air moved in and out with each breath is called tidal volume. So this is an important graph. This is figure 2317, pulmonary volumes and capacities. Now, volumes, we're going to talk about amounts of air that are moved with a certain activity. The capacities are really then when you start adding some of them together. It'll make more sense as we jump in here. So one of the most important volumes we just mentioned is this idea of tidal volume. You might see that abbreviated V sub T, volume, tidal, and that's about 500 mils, right? This is just at rest every time you inhale and exhale. Inhale and exhale. How much air are you moving, right? 500 mils in, 500 mils out. You will notice that that's actually a very small portion of our total lung capacity. So at rest, you're not living up to your potential, right? You're only using a small fraction of your potential lung capacity. All right, a couple other volumes. So we have this one. This is inspiratory reserve volume. And this is the volume of air that can be inhaled after a normal inhale. So, right, normal inhale, normal exhale, tidal volumes, right? Normal inhale. From there up, how much can you inhale? That's inspiratory reserve volume, right? And you'll notice that's quite large. You don't need to memorize all the numbers. You should know 500 mils for tidal volume. But notice inspiratory reserve volume varies greatly, right? Even between males and females. In males, you get somewhere around 3,300 milliliters, so over 3 liters. In females, 1,900 mils, so less than 2 liters. Anyway, that's inspiratory reserve volume. The other volume you should know is the same thing, but on exhalation. That's expiratory reserve volume. Right, or ERV. ERV, IRV. Okay. So if inspiratory reserve is the amount you can inhale after a normal inhalation, expiratory is that volume you can exhale after a normal exhalation, right? So breathing in, breathing out, breathing in, breathing out, and then, right? How much can you possibly exhale? Okay, so that's expiratory reserve volume, right? So those are our volumes. Now you'll see we move into capacity. So we start adding a few of these volumes together. Oh, sorry, I wanted to point out, notice expiratory reserve volume. There's one more volume, residual volume. This is important, notice this. Once you've exhaled as much as totally humanly possible, there is still this residual volume. You will never be able to move this air, right? Basically, if you removed all of that, your lungs would be collapsed, and we don't want to do that. It's really hard to open those alveoli once they kind of smack together. I know, even with the surfactants, it's hard to reopen them. So you always end up leaving, notice that, it's almost it's a little bit over a liter of air sits in your lungs at all times. Now, this is important physiologically because that means even when you exhale as much as you possibly can, right, there's still this whole volume of air sitting in your lungs doing gas exchange. So when you inhale, it's not like all this oxygen from the atmosphere suddenly hits your lungs. It's mixing in with whatever air is still sitting in the lungs, right? And so it's actually not the most efficient way that you could design a lung, but it's what we got, and it works. All right, so there's your residual volume, the amount of air left in the lung after the biggest exhalation possible. Okay, on to capacities, right? We'll just work our way across here. So total lung capacity, right? Notice that this is how much air the lung can possibly hold. It includes residual volume, expiratory reserve volume, tidal volume, inspiratory reserve volume, right? So if you wanted to write that out, though honestly, it's more important to understand what it is, right? It's the total possible volume of air in the lung, but you could say it is IRV plus T sub V plus ERV plus residual volume, right? We just added this and this and this and this together, okay? That is your total lung capacity, right? Notice how that's different. I'm going to skip one. Notice how that's different from vital capacity. Vital capacity includes everything except residual volume. So vital capacity, how would you describe that? It's basically the most, from the point of where you've inhaled as much as possible to where you've exhaled as much as possible, right? So we ignore the residual volume, but it's the amount of lung that we're basically able to use, right? Vital capacity then would be IRV plus T sub V plus ERV. But again, it's the amount of air you can actually move. Inspiratory capacity, right? Inspiratory capacity basically takes vital capacity plus inspiratory reserve. I have no idea what I just said. Tidal volume plus inspiratory reserve volume, right, would be inspiratory capacity. So a normal inhalation followed by that largest possible inhalation is inspiratory capacity. How much can you inhale? Awesome. Expiratory, functional residual capacity is our final one. And functional residual capacity basically says expiratory reserve volume, right, plus residual volume. After a normal exhalation, how much volume do we have in the lung? Expiratory reserve volume plus residual volume. Again, the capacities are all volumes kind of added together. And it's not a bad thing to know. More important, though, to understand what it means. In lab, you'll get a chance to actually, we can't measure all of these volumes, but you'll be able to use a spirometer and get an idea of how some of these volumes are captured. Now, once we know about all of these volumes, we can calculate something very similar to cardiac output. So it's called respiratory minute volume. And we're basically saying, what's the volume of air that the lung can move in 1 minute? So just like cardiac output, it's going to basically be the rate, this time respiratory rate, times the volume of air actually moved, our tidal volume here. So I don't know why they abbreviate it. It's like this V with a dot above it, sub E. This is respiratory minute volume. And that is going to be the breathing rate times the tidal volume. So breathing rate is abbreviated here with an F, and then you know tidal volume is that amount of air, right, that we're moving in a normal breath. And so a very typical respiratory rate would be about 12 breaths per minute. We said a normal tidal volume is about 500 milliliters. What do I do? Breaths per minute. And so if we multiply that, what do we get? That would be about 6 liters. Okay, so that'd be a very normal respiratory minute volume. Now, the one thing to keep in mind is that that is not all air that's going to be part of gas exchange in the lungs. So we also have what's considered this anatomical dead space. When you inhale, air that stays in the trachea or the bronchi that never makes it to the alveoli doesn't get to participate in gas exchange. You breathe it right back out in your next exhalation. So sometimes we're also interested in, well, how much air is actually getting to the alveoli, and so there's a calculation for that as well. We call that alveolar ventilation. That I can at least see, right, ventilation to the alveoli, and that is the breathing rate times tidal volume minus that anatomical dead space, the volume of the dead space. So our tidal volume is still around 500. That dead space is about 150 mils, I think is what they typically use. 150 mils, right? And so that gets us yeah, that's right, 350 mils that actually participate in gas exchange. We'll keep our breathing rate the same, so 12 times 350, don't worry, I already worked it out, 4.2 liters, right? So it's less. Here's the deal. You should be able to do this, right? You should know what respiratory minute volume is, how you'd calculate it. I'm not going to ask you to memorize that dead space, but realize that it's there and that you might see someone talking about this alveolar ventilation. Now, to think about these volumes and capacities in actual living organism, right, do consider tidal volume is basically what we would consider quiet breathing. And recall, you're really only going to use 2 muscles to do that. They call these primary muscles of inhalation. That includes the diaphragm and the external intercostal muscles. Remember those little muscles between ribs? So basically you're lifting the ribs, you're depressing the diaphragm, increasing the volume, and air flows in. Exhalation, quiet exhalation, is completely passive. It's just due to the recoil of that lung tissue. But notice, if you want to do any of those bigger volumes, if you want to find inspiratory reserve or expiratory reserve, there's a lot of accessory muscles. You don't have to know all of these, but realize they exist. For inhalation, you're thinking anything that's going to help lift that rib cage. Sternocleidomastoid was one of your muscles in AMP1, pectoralis minor, serratus anterior, right? You might recognize those. And then for exhalation, you're looking at the internal intercostals, some of your obliques, a lot of abdominal musculature, right? You can kind of picture that. all squeezing together abdominal muscles to exhale more effectively. All that talk of pulmonary ventilation, it's important to note that we got there because we were saying external respiration had three main factors. Pulmonary ventilation, it also includes the diffusion of gases as well as the transport of those gases. So we're to number 2 here, the diffusion of gases. Now, this goes into a little bit of physics, right? So how gases diffuse are ruled by a couple of laws, right? And when we talk about gases diffusing, we mean that oxygen moving from the alveolus into the blood and the CO2 doing the opposite. So the diffusion of gases, the two laws that we have to deal with are Dalton's law and Henry's law. Okay, so Dalton's law, I call it the duh law, but Dalton's law basically says when you're looking at atmospheric pressure, right, that pressure, that column of air on top of you, each individual gas contributes to that pressure according to the percentage it makes up in the atmosphere. So think about this. So if you're that little guy, there you are, standing there with that column of air on top of you, right? We said that was an atmosphere, or 760 millimeters of mercury. Now, when we look at gas in the atmosphere, it is about 79% nitrogen, so almost 80, right? 79% nitrogen, maybe actually be N2. It is about 21% oxygen. This is, of course, the one we're going to be most interested in. You should absolutely know that the atmosphere is 21% oxygen. And then we have, of course, some water vapor, that's like 0.5%. We've got some CO2, but notice 21 and 79, that's 100%, right? This is really small, 0.04%, 0.5%, right? So those are small numbers. This is the one we're interested in, getting it into the lung, into the alveoli, and then into our blood. Okay, so basically what you would do here is you'd say, okay, well, if I know I have 700 millimeters of mercury of total pressure, basically 79% of that pressure is coming from nitrogen. I already wrote this down. So that's about 600 millimeters of mercury, right? Oxygen, always 21%. 159 millimeters of mercury, right? And then these are really tiny, like 0.3 and 0.03, something like that, right? Really low amounts, but there you are, 760. So Dalton's law just says that the partial pressure, right, of each, this would be partial pressure of each individual gas. If you add them together, it gives you the overall pressure. Duh. So Dalton's law. The thing to keep in mind here, right, is these percentages don't change. In the Earth's atmosphere, in this room, there is always, unless you've done something really strange, there is always 21% oxygen. And you say, well, wait a second, there's less oxygen when we're not at sea level. But notice what happens. We're just gonna make a little mountain here, right? And so if our little guy here climbs on top of a mountain, right? The top of the atmosphere stays in the same spot. The column of air sitting on top of him is smaller, but it is still 79% nitrogen and 21% oxygen. It's always 21% oxygen, but the overall pressure has changed. So he's on top of our mountain, let's call it a 14er here in Colorado, the overall pressure at 14,000 feet is 460 millimeters of mercury. 21% of that, don't worry, I've done the math, but you can check me, is 96.6 millimeters of mercury. Now, here's why this is important, right? 159 millimeters of mercury is the number that you'll see the book using. It's assuming everybody lives at sea level. And so notice when they show the PO2, that is the partial pressure of oxygen, they're showing it at around 100. Now, you're like, that's not 159. But recall, by the time you get to the alveoli, you've already mixed in to that residual volume, right? We said all the air isn't exhaled each time, and so you're kind of getting diluted with some carbon dioxide and stuff, and that pressure, you have a lower percentage of O2 in your lung than there is in the room. So they're using this number 100. Notice though, if you're on top of a 14er, you're already below that. And so by the time you kind of do some fudging and you go, well, what if now the partial pressure of oxygen in the alveoli is only 70, right, or something like that? It's going to make it feel, right, like there's less oxygen. There is less oxygen. The partial pressure of oxygen is lower at altitude. The percentage has not changed, right? The percentage of the atmosphere is always 21%. Okay. Now, this becomes important because when we think about the diffusion of gas from the alveoli into the blood, or vice versa, remember diffusion, we're always going from an area of high concentration to low concentration. But what happens is if your area of high concentration and low concentration aren't that different, right? The gas will move, but it's pretty slow. Right? If instead you have a very steep concentration gradient, that gas is going to diffuse very rapidly, right? And that's what we want to have happen at the lung to move that oxygen into the blood quickly. So the difference between going from 100 of a partial pressure of oxygen, and they're showing here in the blood about 40, that's pretty steep, right? Oxygen moves in. If you're up at altitude and we decided, maybe this is more like 70 to 40, not as steep. So we're still moving oxygen, but it's not as quick. Okay, so Dalton's law, again, is saying that each gas, nitrogen, oxygen, water vapor, whatever, each gas contributes to the total pressure in accordance with its abundance, right? Its percentage. And oxygen is the key one here. It's always 21%. Okay. And you're like, you haven't even gotten to Henry's law. Henry's law basically talks about how gases move into a liquid. We'll keep this one quick. This one's not quite as important to us. So only in that we don't really change it. So Henry's law basically says a couple things, right? If you think about, say, a river, right? We know there's oxygen up here in the air, and we know that the river is water, okay? But oxygen, as it bumps into the surface of that water, it can diffuse, right? Some oxygen moves in to our river, which is good for our fish. Now, not all the oxygen, right? Some of it just bounces off the surface. Each gas actually has a different, we call it like a coefficient of how it dissolves. Some things are much more soluble in water than others. And you don't have to memorize any of that. It doesn't change. The other thing that it says is how it moves into the liquid has to do with, again, the pressure kind of sitting on top of it. So again, at sea level, if you have your 159 millimeters of mercury oxygen, that's going to push more into the river than if you're up, a high mountain lake where you have that lower pressure, partial pressure of oxygen to start with, less is going to move in. Same thing, right? You have a glass of water sitting on your counter, very low room pressure of CO2, but some can dissolve into that water. Most of it bounces right off the surface. But you put it in your soda stream and you up the pressure of CO2, right? And next thing you know, you're forcing all these bubbles of CO2 into the water, right? So the pressure in the atmosphere is going to make a difference in how much of that gas moves into the liquid. So that's all Henry's law is talking about, is how gases diffuse into liquid and how that is associated with the pressure. You're going, okay, river, soda stream, what? Your plasma, don't forget your plasma, it's like a river. Your plasma is liquid, and so different gases are going to diffuse more or less easily into the plasma. But it's a constant. So it's not something we change, other than if we go to altitude or we go to deep sea diving, whatever, and we change those pressures that are pushing gases into the liquid. Okay, confusing physical laws aside, what this is trying to tell us is that gas exchange at the respiratory membrane is extremely efficient. Gas exchange at the respiratory membrane is efficient. Okay, here's why, right? So one, we were talking about how the steeper the gradient, the more rapid that gas is going to diffuse. So a steep concentration gradient is fast, right? So again, at sea level, we typically have pretty good differences between the alveoli and the capillary blood supply. Remember also that that distance is very small, that the respiratory membrane is thin. Right, we have very short distances to cover. Okay. The gases that we're trying to move, oxygen and CO2, are both lipid soluble. And so remember, the endothelium has two cell membranes, one on each side, that the gas needs to move through. So does the alveolus, right? So just a couple simple squamous cells to move through. But they don't, right? When you're lipid soluble, you don't even need a transport protein, right? Those can get maxed out, how much you can possibly move. If you are a lipid soluble molecule, like oxygen, remember these tails in a phospholipid, they're lipids. They would repel water-based substances, water-soluble things, which is why those need channels. This lipid-soluble molecule just goes straight through that phospholipid bilayer. So oxygen and CO2 are both lipid-soluble. We also, keep going over here. We have this huge surface area, right? When you lay the alveoli out, we said that that ends up being basically half a tennis court. And then the other thing to keep in mind here is that there's this big coordination in the lung between airflow and the blood flow. So remember when we were in the vascular system, we said, oh, well, capillaries, they're not all full all the time. And what happens in the lung is the portions of the lung that are getting the best airflow, we get the best blood flow to kind of match up with that. So you might say that the blood flow and airflow are coordinated, okay, in order to help us move these most efficiently. Now, we don't have the most efficient lung in the animal world. Birds are actually much better, but what we have is extremely efficient. And then finally, for external respiration, right? We've covered pulmonary ventilation, we've covered how gases move, how they diffuse right, from the alveoli into the blood. And then third thing was how oxygen and CO2 are actually transported. Oxygen is transported in the blood primarily bound to hemoglobin, right? So we can say hemoglobin, right, plus oxygen, right? They'll actually call this oxyhemoglobin. Okay. Recall, each of your red blood cells has so many hemoglobin molecules that you can carry around 1 billion oxygen molecules at a time. Now, the key thing to keep in mind, so there's your oxyhemoglobin, the key thing to keep in mind is that oxygen is reversibly bound to hemoglobin. And I say this is important because if hemoglobin had a big attraction for oxygen, right, and grabbed onto it nicely at the lung, but never let it go, it wouldn't work, right? This is such an amazing molecule because in areas with high partial pressure of oxygen, that would be the lung, right? Recognize this. In the alveoli, we were saying it was around 100 millimeters of mercury, okay? What happens to our saturation? We're almost 100% saturated, meaning that almost every single hemoglobin molecule is carrying 4 oxygens, right? That's how we get this saturation. But it's reversible. So notice what happens. Once that blood starts circulating away from the lung, say it travels, the blood travels over to like where a tissue is working, and the oxygen molecules have already been taken out of the blood, we have a much lower partial pressure of oxygen, say in this working muscle, and notice what happens. We get this lower saturation. And you're going, okay, well that makes sense. But this really steep line tells us that some small changes in the partial pressure of oxygen can lead to big changes in saturation. So think about it, this curve ends up confusing a lot of people, but just think about it at high oxygen concentrations, you're very highly saturated. You're carrying lots of oxygen. Down here, you're letting it go. You're delivering it to tissues. And when that blood comes back around to the lung, it's going to pick up oxygen again, but then it lets it go. Okay, let me know. We can talk about that more. There are a couple things that affect hemoglobin's ability to be saturated with oxygen. So one of those is pH. They call this the Bohr effect. Some old dead dude that discovered this, right? So typically we say, hey, blood pH should be 7.4. So the center line is the typical oxygen hemoglobin saturation, right? Notice what happens in areas that are more acidic, and this isn't a huge change, but what happens here is if you looked at the, let's do a dotted line here. If you looked at the same partial pressure of oxygen, notice what happens, okay? At a lower pH, you're not gonna hold as much oxygen, okay? So we say that a decreased pH causes a decreased affinity for oxygen. Think about that. And the other way to think about it, they call this a right shift on the oxygen hemoglobin curve. Think about this. At a working tissue where you're making lactic acid and you have a lower pH, you start dropping more oxygen. You decrease hemoglobin's affinity for oxygen so it gets delivered. Okay? A left shift would be the opposite. So at a higher pH, you grab more oxygen. Right? So working tissues are essentially setting up this situation where we have this this auto-regulation of delivery. Okay? Temperature has the same effect. Notice that right shift again at warmer temperatures. So higher temps lead to a decreased affinity of hemoglobin for oxygen, which again means at working tissues where it's warmer, you're delivering oxygen. At cooler tissues, like the lungs, you increase the affinity, you pick up more. It's this crazy molecule. Okay, last one, and then I'll move on. This graph is showing fetal hemoglobin. Right? So as a fetus, you actually are producing a slightly different protein, a slightly different version of hemoglobin. This is wild. And notice fetal hemoglobin is a left shift compared to normal adult hemoglobin. That means it has a higher affinity for oxygen, right? At that same partial pressure of oxygen, fetal hemoglobin is much more saturated than adult hemoglobin. It's so you can steal oxygen from mom, right? You're not using your own lung yet, and so the blood you're trying to grab from mom maybe isn't quite as oxygenated, and so you're gonna hog it. That's crazy. Okay. So oxygen is carried reversibly bound to hemoglobin. What about CO2? Okay, CO2 is carried three main ways in the blood. So when that CO2, and let me remind you, CO2 is coming from these working tissues. They've done cellular respiration, CO2 is the byproduct, and now we need to move it into the blood, carry it to the lung to get rid of it. Okay, our three different ways here are CO2 is carried, some in the plasma, right? CO2 actually diffuses much more nicely into liquids than oxygen. So there's a minute amount of oxygen being carried in the plasma, most is on hemoglobin, but when we get to CO2, it's about 7% of the CO2 just dissolves in the plasma and gets carried through the body. Cool. The rest of it, 93%, diffuses into the red blood cell. But what we'll see is, still out of 100%, right? 23% of our blood, 23% of our blood binds, of our CO2 binds to hemoglobin. And again, this is reversible. And they call that, right, so you can do hemoglobin plus oxygen, CO2, carb-aminohemoglobin. There's a mouthful, right? Carb-aminohemoglobin, 23% of our blood. That still leaves us with 70% of our CO2, and this is going to be your favorite one. So 70% of your CO2 goes through this chemical conversion process, and here's what it looks like. Well, let's just put this out first. 70% is converted to carbonic acid. Right, that's what they're showing here, but let's look at this whole process. So basically what happens in the red blood cell, you take CO2 and you add it to water that's just hanging out in the cell, right? And we can produce carbonic acid, H2CO3. Now look at this. If you're not feeling great with chemistry, there's your two H's, there's your C, and then 1, 2, 3 oxygens, right? So just make sure you account for everything. And you have H2CO3, which is carbonic acid. Okay, but we don't stop there. Carbonic acid is going to dissociate. It's going to fall apart, and it falls into a hydrogen and HCO3 minus, which is bicarbonate. Okay. Now, the hydrogen stays inside of the red blood cell and actually often binds to hemoglobin. If the hydrogen went out of the cell, we would be changing the pH of the blood really rapidly, and so we don't want to do that. So the hydrogen is going to bind to hemoglobin. Hemoglobin then is a nice buffer. The bicarbonate, check this out, the bicarbonate actually leaves the red blood cell, right? It goes out into the plasma where there's plenty of room. Right, out to the plasma. It actually gets exchanged for a chloride. I'm not too obsessed with that detail, but it does occur to make sure that we don't skew the electrical ratios inside of the cell. Okay, so picture this. At your working tissue where there's lots of CO2, it's pouring into the red blood cell, combining with water to make carbonic acid, immediately splitting into hydrogen and bicarbonate. That goes out into the plasma, and all of this blood, right? So this red blood cell with some of its CO2, plasma has CO2, plasma now has a lot of bicarbonate, this is flowing through the body. When it gets to the lung, we need to exhale CO2. All of these reactions are reversible. So when this gets to the lung, the bicarbonate comes back into the cell, the hydrogen comes off of the hemoglobin, those two join together to make carbonic acid, right? Carbonic acid can split into water and CO2, and you exhale. This is crazy. Life is crazy. Okay, so there's this image in your textbook that kind of lays all of this out. I love this image. It's image 2324. Students get lost. Here we are in the alveoli. There's oxygen. That oxygen, a little bit goes into the plasma, but most of it is going to bind to hemoglobin, right? When we travel through the body to the cells that need oxygen, oxygen comes off hemoglobin, diffuses out of the cell, out of the red blood cell, is delivered to the cells who do cellular respiration, right? Now we have CO2. CO2, 7% in the plasma, 23% attached to hemoglobin, and the remaining 70% combines with water to form carbonic acid, which splits into hydrogen and bicarbonate. Here's the hydrogen attaching to hemoglobin, and here's the bicarbonate leaving the cell. All of this flowing through the body toward the lungs. Here at the lungs, we reverse everything. Bicarbonate comes back in, joins with hydrogen to make carbonic acid, which splits into water and CO2. We can now exhale our CO2. The hemoglobin that was carrying CO2 releases it, and the CO2 also leaves the plasma. Cool. As far as the control of respiration, some of it is absolutely localized, right? So those working tissues where we've got increased levels of CO2, decreased levels of oxygen, that's actually going to, we saw this in the cardiovascular system, those are local regulators that would cause vasodilation, right? Trying to increase the delivery of blood flow. We also see in the lungs that the area of lung, the alveoli that have the highest oxygen, are the alveoli that get the most blood flow. So those higher levels of oxygen are also opening blood vessels in the lung. It's a little weird in the body. It's low levels of oxygen that would help vasodilation, and actually in the lung, it's those higher levels. Isn't that cool? We also see that as the alveoli start filling with CO2, right, the alveoli that we're actually diffusing CO2 in, we get good bronchodilation to those areas to help us dump more of the CO2. Now, the brain, of course, is also involved in respiration, right? So we've already, no, that was cardiovascular, we talked about that. Here we see basically the medulla and the pons being involved in the regulation of respiration. So without getting too crazy, the medulla, terrible marker. So the medulla oblongata is involved here. It can both directly sense cerebral spinal fluid, oxygen, CO2 levels, but it also does rely on those same chemoreceptors. That we saw in the aortic and carotid bodies. chemoreceptors are in the bodies, and those are relaying the messages to the medulla, so the medulla can change the respiratory rate. So the pace of breathing, right? So the medulla is really the main one. We do see these regions in the pons. I don't care that you get into aponeustic and pneumotaxic centers. Really, when I think about it, it's the pons has this ability to kind of modify what the medulla has already decided. So the pons kind of makes adjustments to both pace and the depth of breathing. Now notice, right, both of these are in the brainstem. So you can have brain injury to some of these higher regions of the brain, and we'll continue to maintain these vital kind of life-saving measures down here in the brainstem. The brainstem is really who you don't want to injure. These higher centers can make adjustments, right? I can tell you to hold your breath, and you can override the breathing rate that the medulla has set for you. But for the most part, this is going to be pons and medulla. The other thing I would point out, maybe I should think about that with chemoreceptors, is it is really, I think, key to understand that it's CO2 levels that drive breathing rate. So we think we breathe because we need oxygen, but it's actually the buildup of CO2 and that change in pH that we pick up on by these chemoreceptors that tells the medulla and the pons how to adjust our respiratory rate.